Hi guys, my name is Danielle. Welcome to UVillage. In this video, we will be discussing frequency distributions. A frequency distribution is a table in which the data is grouped into classes and the number of values, which we refer to as frequencies, is recorded for each of these classes. The purpose of constructing a frequency distribution is to gain some insight into the distribution of these values within the classes. The following is an example of a frequency distribution. From this table, we can see that 25 employees earn between 0 Rand and 2,500 Rand, whereas 25 employees earn between 7,500 Rand and 10,000 Rand. Here, the data is grouped into classes, and the number of times each value falls into those classes is recorded. This represents a frequency distribution. There are 6 steps involved in constructing a frequency distribution. In order to understand these steps, I'd rather take a look at an example and go through each step one by one with you. The first step in constructing a frequency distribution is to determine the range. This is done by calculating the maximum minus the minimum. For this data set, the maximum value was 77 and the minimum value was 12. So that gives us a range of 65. The next step is to calculate the number of classes we will have in our frequency distribution. And that's calculated by using what we call Sturge's rule. 1 plus 1.44 ln of n, where ln is a log to the natural base and n is our sample size. So here, our sample size, which is the number of values that we have, is 50. So using this in our formula, we get that the number of classes, which is represented by k, will be approximately 6,63. So this is telling us we have 6 and a bit classes. So we don't want 6 and a bit classes, so what we always do is round up. So for the number of classes, no matter what our decimal place is, we have to round up to the nearest whole number. The last step in this section is calculating the class width. And that is done by taking the range of 65 and dividing by our number of classes, 7. So that's going to give us a value of 9,3. But once again, we can't have a class width that is 9.3 in length, so rather round up to the nearest integer. And always round up. So that will give us a class width of 10. So for this example, we know that we're going to be working with 7 classes, each of a width of 10. The fourth step is to calculate the very first value in your first class interval. And this is done by taking a value that is just lower than your minimum value in your data set. There is no strict rule on what this value should be, so to make things a bit easier, I'm just going to take it as 10. So that's going to be my first class interval's lower value. The next step, the fifth step, is to calculate the lower values of all the next classes. So this is your lower value of your very first class, and you know we have 7 classes. So to calculate the lower value of your next class, all we do is add our class width of 10 to this value. So the lower value of the second class will be 20. And likewise, for the next class, you add your class width to that value. So all your lower values are going to be 10, 20, 30, 40, 50, 60, and 70. Because we know we have a total of 7 classes. The final step is to calculate your upper values of all these classes. And this is done by just taking 1 unit less than these lower values. So the value less than this lower value will be 19. Then the value less than this lower value will be 29, and so on. So this value will be 39, then 49, then 59, 69, and then obviously this class, the next class's lower value would have been 80, so it goes up to a value of 79. And those are your class intervals for your frequency distribution. Now we can record the frequencies that fall into each of these classes. So if we have a look at our data set, you'll see two values, 12 and 15, that fall into this class interval. So that means there are two values that fall into that class interval, so the frequency is 2. Then likewise for the rest of them, there would be 4 values that fall into that interval, 7 values that fall into that interval, 10 in that, 16 in that, 8 in this, and then 3 in your very last class. Now this would be your frequency distribution. Now remember, what is the data actually telling us? These were the percentages for a stats mark, and these were the number of students that got these results. These are referred to as your class intervals, and these are your frequencies. What we have here is gaps between our upper class value of one class and our lower class value of the next. These are referred to as class limits. And what happens if we obtained a mark, say, of 19.5%? Then which class would these fall into? Then we would have to recalculate these into class boundaries. Class limits, which is what we have here, is referred to as inclusive classes. Both this value of 10 and 19 will fall into this class. But if we transform this into other class values, it would be known as class boundaries. And this is done by taking the average of this gap and adding them all to these upper values and subtracting them from these lower values. So let's have a look. The gap between 19 and 20 is obviously going to be 20 minus 19, which gives us a value of 1. Averaging this gap is going to give us a value of a half, 0.5. So if we subtract this from all of these lower values, so for the first class, we will get 10 minus a half, gives us 9.5. The next class would be 19.5. The next would be 29.5, and so on. Then if we add that value to all the upper classes, we would get a value of 19.5, then 29.5, and then 39.5. Now obviously if we continue in that same direction, we'll end up with class values that what we call are continuous. There is now no gap between a value of 19.5 and the next value of 19.5, which means no values in a data set that perhaps contain decimal places would be left out. These are referred to, as I mentioned, as class boundaries. These are class limits with a gap, and these are class boundaries with no gap. Class boundaries are known as exclusive classes. Because there are two values here, then where would a value of 19.5 fall? Would it fall into the first class or the second class? So a rule of thumb is that it always falls into the next class. So a value of 19.5 would fall into this class. A value of 29.5 would obviously fall into this class. That is the difference between class boundaries and class limits. There are a number of things that we can calculate from a frequency distribution. Let's take a look at the first few classes from the previous example. One of these things that we can calculate is the class midpoint, and that is simply the middle value of your classes. And that is done by taking the lower class value of one class and adding it with the upper class value. Then we divide it by 2, and that will give us our midpoint. So for the very first class, we get a midpoint of 14.5. Doing that for the rest of the classes, we'll get a value of 24.5 and 34.5 in the next class. These are just referred to as the midpoints. The next thing we can calculate is the relative frequency. As the name suggests, relative frequency is the frequency of a class relative to the sample size. For this example, our sample size is 50. Remember, we are only working with the first 3 classes for this example. So to calculate the relative frequency for this class, we simply take the frequency of the class and divide it by the total sample size. And that should give us a relative frequency for this class of 0,04. And likewise, to calculate the relative frequency for the next classes, we take the frequency divided by the total sample size. So we should get a relative frequency of 0,08 for the next class and 0,14 for the third class. That is relative frequency. Now we can calculate the relative frequency percent. And that's simply by converting the relative frequency into a percent. So recall, the relative frequency for this first class was 0,04. To change it into a percent, we simply multiply it by 100. So we get that the relative frequency percent for this class is 4. Likewise, for the rest of the classes, we get that the relative frequency percentage for this class was 8, and for the next class is 14. This tells us that 4% of the values in your dataset fall between 9.5 and 19.5, whereas 8% fall between 19.5 and 29.5. The last thing that we can calculate for a frequency distribution is cumulative frequency. Cumulative frequency is the number of values in your dataset that is less than or equal to the upper class boundaries of your class intervals. For example, the cumulative frequency for your first class would be 2. Because it's your first class and there are 2 values that lie in this class, then the number of values in your dataset that is less than or equal to 19.5 would be 2. Whereas the second class, your cumulative frequency is the number of values in your dataset that is less than or equal to 29.5. And since 4 values fall into this class and 2 values fall into this class, we'll have a total of 6 values that are less than or equal to 29.5. Similarly, for your third class, we'll have a total of 2, 4, and 7 values that are less than or equal to 39.5. So that gives us a total of 13 values in our data set that are less than or equal to this upper class boundary of 39.5. That would be cumulative frequency. Now that we have our data summarized in a frequency distribution, there are 3 ways in which we can represent this data graphically. There's a histogram, a frequency polygon, and a less than ogive. Let's have a look at a histogram. A histogram for a frequency distribution graphs the class boundaries corresponding to the frequency for each of those classes. On your x-axis, your class boundaries would be represented, and on your y-axis, you would have your frequency. For this example, on marks for 50 students, the resulting histogram would be as follows. The next graphical representation is a frequency polygon. A frequency polygon graphs now the class midpoints for each of the classes corresponding to the frequency. So in this case, our x-axis would be our class midpoints, and once again, our y-axis would be the frequency. So at an x value of 14.5, we'll have a corresponding y value at 2. So we just put a dot in that space. But a frequency polygon has to be anchored to the x-axis. And this is done by calculating the 2 anchor points that would be on the x-axis. These are calculated by taking the very first midpoint and subtracting a class width of 10, which means at a value of 4,5, therefore at a value of 4.5 on the x-axis, our frequency polygon will be anchored there. Then to find the very last anchor point, we have to take the last class midpoint of 74,5. Now add a class width of 10, and we will get that our frequency polygon will be anchored to the x-axis at a value of 84.5. The resulting frequency polygon for this example would be as follows. The last form of a graphical representation of your frequency distribution is a less than ogive. A less than ogive graphs the class boundaries corresponding to their cumulative frequency. The very first point that we'll start with is the class boundary of 9.5. What is the corresponding cumulative frequency for this value? It would be 0. There are no values in your data set that are less than or equal to 9.5, as it is the first value in our first class. Then we can move on to the next upper class boundary. What is the cumulative frequency for this class? It would be 2. So at a value of 19.5, we would graph a cumulative frequency of 2. Now for the next class, we do not repeat a value of 19.5 as it has already been done in the previous class. So we move on to the next upper class boundary. So the corresponding cumulative frequency for this value would be 6. Likewise for the next couple of classes. All the lower class boundaries will have been done by the previous upper class boundaries values. So therefore, we graph the upper class boundaries of all the next classes corresponding to their cumulative frequency. Your very last value of 79.5 should end at a cumulative frequency of 50, which means that there are 50 values less than or equal to 79.5, which happens to be all the values in your data set. The resulting ogive for this example would be as follows. We have just concluded frequency distributions and their graphical representations. The main purpose of graphing a histogram or a frequency polygon for a frequency distribution is to get an idea of the clustering pattern of the values in the data set. In other words, to look at the shape of their distribution. Let's have a look at some different shapes. The first shape we'll look at is a symmetric bell-shaped distribution. This shape occurs when the majority of the values fall in the central portion of the scale with fewer values further away from the center on either end. An example of this shape would be heights. There's a norm height which most people follow, but then to the left of that height, there are not too many short people, whereas to the right of that height, there are not too many tall people. That would be a symmetric bell-shaped distribution. The next shape is uniform shape. This shape occurs when every value in the dataset occurs the same number of times. An example would be tossing a coin a large number of times. We would expect to see the same number of heads as tails. The next shape is the bimodal shape. This shape occurs when there are two distinct peaks in the dataset. An example of this would be if we recorded the heights of males and females in one set of data. Females are generally shorter than males, therefore there would be a peak at a lower height for females and then a peak at a higher height for males. Next we have a positively skewed shape or a skewed to the right shape. This shape occurs when the majority of the data, where the peak occurs at the lower end of the scale and fewer values occur at the upper end. An example of this shape would be the time it takes to serve a customer at a supermarket. For most customers, the service time is quite short. The longer the service time, the less number of customers there are. The last shape is negatively skewed data, or skewed to the left. This shape occurs when the majority of the data, or the peak, occurs at the upper end of the scale, with the fewer at the lower end of the scale. For example, a statistics test where the majority of the students did well and scored a high score, with few students doing badly and achieving a low score. Many students get very confused between the difference between positively skewed data and negatively skewed data. So I find that the best way to remember it is remember their alternative name. Positively skewed is another way to say skewed to the right. Negatively skewed is skewed to the left. So where is the tail end of your graphs occurring? For positively skewed data, your tail occurs to the right, so it's positively skewed. And for negatively skewed, your tail occurs to the left, which means it would be negatively skewed. That's the end of frequency distributions. Thank you for watching UVillage.